So section 5.6 covers some further counting techniques. So the first thing I want to go over is how to count when it comes to working with tossing coins, routes through a city, or drawing balls from an urn. So an experiment consists of tossing a coin 10 times and observing the sequence of heads and tails. How many outcomes are possible? How many different outcomes have exactly 2 heads? How many different outcomes have at most 2 heads? Feel free to sketch this out if you wish, but I am going to show you guys the way to calculate these things using the multiplication principle and permutations and combinations that we've already learned. So a possible outcome for tossing a coin 10 times could be heads, tails, heads, tails, 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 heads, tails, heads, tails. So each coin has 2 possible outcomes. I talked about this before. So there's going to be the 10th power, because we're flipping the coin 10 times, possible outcomes. So there's 1,024 possible outcomes. My second question was, what if there are exactly 2 heads? So because there are exactly 2 heads, where it's the 10 choose 2, so I'm going to have 10 times 9 divided by 2 times 1. At most 2 heads means there can be 2 heads, 1 head, or 0 head. There's only one possible outcome with no heads, and that's if it's all coins or 10 tails, so that's good to know. C of 10 times 1 is 10 possibilities with exactly 1 head. And C of 10 choose 2, there are 45 outcomes. So we're going to have 1 plus 10 plus 45, which is 56. So there's 56 possible outcomes with at most 2 heads. At least 2 heads means there can be 0 heads or 1 head. So there are 1 plus 10 possible outcomes with 0 or 1 head. Because there are 10,024 outcomes total, we're going to take that and subtract the 11. So there's 1,013 possible outcomes with at least 2 heads. Okay? At least means there must be at least 2, but there could be 3, there could be 5, there could be 7. So that's why this number is so large. So from the same experiment, and I'm tossing a coin 6 times and observing the sequence of heads and tails, how many different outcomes have more heads than tails? So I just had found that 20 have exactly 3 heads. I need to know how many have 4, 5, or 6 heads. So I'm going to take 6 choose 6, 6 choose 5, and 6 choose 4. And that's going to tell me how many outcomes have more heads than tails. Because I've got an even number. It's going to have to be those with 4, 5, or 6 heads. Well, 6 choose 6 is 1. 6 choose 5 is going to be 6 times 5 times 4 times 3 times 2 over 5 factorial, which is going to cancel out all this, so it's going to be 6. And then 6, 5, 4, 3 over 4 factorial. That's going to be 6 times 5 over 2, which is 15. So how many different outcomes have more heads than tails? That's going to be 15 plus 1 plus 6, which equals 22. Now, how many outcomes have at least 2 heads? At least 2 heads. That means I could be all of this plus that which has 3 heads and that which has 2 heads. But we could also do 6 choose 2 and 6 choose 1. Well, 6 choose 1 is just going to be 6. 6 choose 2 is just going to be 6 times 5 divided by 2, which is 15. So I take 2 to the 6th minus 15 plus 6. 2 to the 6th is 64. I'm pretty sure. Let me double check. 2 to the 6th is 64. So I have 64 minus 15 minus 6 equals 43. So there are 43 different outcomes with at least 2 heads. Next, I would like to know how many different outcomes have at least 2 heads. So that means it could have 2, 3, 4, 5. It just can't have 0 or 1. So I need to find the combination of 6 choose 0 and combination of 6, 1. Well, 6, 0 is going to be just 1. So it's going to be over 0 factorial, which is going to give us 1. There's only one way to choose no tails, right? That no heads, that'd be all tails. And then 6 choose 1, it's just going to be 6. So there are 7 ways to get less than 2 heads. So I'm going to take our entire sample size, which is 64, because that's 2 to the 6th. And I'm going to take 64 minus 6 minus 1, and that's going to give me 57. So there are 57 different ways of having at least 2 heads. Next, I want to talk about walking through a city. So a tourist wants to walk from point A to B, shown on the maps below, and there's no backtracking allowed. So let's say S is walking a block south and East is walking a block east. So the 2 possible routes shown in this map could be designated as south, south, east, 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 southeast, and south, east, south, east, south, east, east, south. Oof. All routes are a string of 7 letters, 3 of which will be S and 4 of which will be E. So selecting a route is the same as selecting where the string of the 3 S's will be placed. Therefore, the total number of possible routes from A to B is 7 choose 3, which is 7 times 6 times 5 over 3 times 2 times 1. So let's look at an example. How many routes are there from A to B? So this is east, south, south, east, east, south, east, south, south, east. So this is a string of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be 10. Oh, you can't see the blue very well, can we? This is going to be 10. Choose, how many S's do I have? 1, 2, 3, 4, 5. Very cool. So this is going to be 10 times 9 times 8 times 7 times 6 over 5 factorial. That's a lot of different ways. This leaves me with 252 possible routes. Next, an urn contains 25 numbered balls, 15 of which are red and 10 are white. A sample of 5 balls is to be selected. How many different samples are possible? How many different samples contain all red balls? How many different samples contain 3 red balls and 2 white balls? So let's go through these examples. So a sample is just an unordered selection of any 5 balls out of the 25 that are in my urn. So this is the possible way I could select any unordered selection of balls from my urn. From a sample of all red balls, we have to select exactly 5 from the 15 red ones. So 15 choose 5 is 3,003. So there's 3,000 ways I could select 5 from the already existing 15. To form the sample with 3 red balls and 2 white balls, we got to select 3 red balls from the 15 red balls, or we have to select 2 white balls from, then we have to select 2 white balls from 10 white balls. So we use the multiplication principle to give us this. Let's work through an example. An urn contains 12 unnumbered balls, 8 of which are red and 4 are white. A sample of 4 balls selected. How many different samples are possible? Well, that's going to be 12, choose 4. Choose 4 is going to be 12 times 11 times 10 times 9 over 4 factorial. That gives us 495. So there are 400 different 90 samples I could possibly choose. How many samples would contain all red balls? Well, I have 8 red balls, and I would need to pick 4 from that sample. So that's gonna be 8 choose 4, which is 8 times 7 times 6 times 5 over 4 factorial. So if I have 8 choose 4, that gives me 70. So out of my 495 possible samples, 70 of them would contain all red balls. So how many samples contain 3 red balls and 1 white ball? That's going to be the probability of 8 choose 3 times the probability of 4 choose 1. So probably of 8 times 3, this is going to be 8 times 7 times 6 over 3 factorial, which is 6. So let's do the 8 times 7, which is 56, times probably of 4 choose 1. That's going to be 4 over 1 factorial, which is just 4. So I have 56 times 4. That's going to give me 224 samples. Now, how many different samples contain at least 3 balls? This is a poorly worded question, kind of a trick question. They don't tell you what color. All the samples contain 4 balls, so it's going to be all of them, all 495. My next question is, how many samples contain a different number of red balls than white balls? So really what I need to know first is how many have 2 red and 2 white, and subtract that from our total number of samples. So there were 0 ways to get at least 3 balls out of our 495 samples. Oh, contain at least? Yeah, no, it's 495. That at least wording trips me up every now and again too. So there are 490 ways to get at least 3 balls. For this last problem, if I know how many samples have exactly 2 red and 2 white, I'll be able to solve this problem. So I'm going to go ahead and clear me a little bit more space and change color while we're at it. So this is going to be another multiplication principle problem. I have P of 8 choose 2 times P of 4 choose 2. That's 8 times 7 over 2 factorial times 4 times 3 over 2 factorial. That's going to give me 8 times 7 divided by 2. 56 divided by 2 is 28 times 6. So 28 times 6, because 4 times 3 is 12 divided by 2 is 6, is 168. If I take 495 minus 168, that gives me 327. So there's 327 samples that contain a different number of red balls than white balls.